Now that we understand how this works, let us see how it is implemented here. So we have, corresponding to our function calls here and here, imagine what will happen. So this is a ripe situation for the use of a stack. Now, who can tell me what is a stack? It is actually a first in last out memory, right? Or a last in first out memory, LIFO, right? So as you can imagine that when we call f from main and it goes, the control goes to f and then comes back here, we must be storing some information about where to come back and where to go. So basically we use something called a call stack. It is a type of a stack which stores the addresses of functions to return to. So how does that work? Let's just make a very clear depiction of that, or try to make it much clearer than this. So let's say this is main. This is at position X. Correspondingly, let us say this is the control sequence here. So the control starts executing at X. At this point of time, there is a call to F, and this is say line Y, and this is say line Y plus 1. So at line Y, the control jumps to, now let us imagine that F is situated. Now obviously, as you can imagine, memory is just only one memory is there. Okay, so it's all a continuous part of memory. So this is all there. Now let us say F is situated at this point, which is say Z. Z is the address. These are all addresses. These are all addresses, memory addresses or locations. Addresses. Okay, so these are the addresses. Now this main function starts from the X address, and then there's a call to F at Y, and the next address Y plus 1 is where we are going to come back, and the Z function is residing at the position, or so beg your pardon, sorry, and the F function is residing at memory location Z, and it is finishing at, let's say, Z plus P, and from Z plus P it is coming back to Y. So each time there is a call, it goes from wherever it is being called, it goes to Z. For example, if there is another call to F here at say position, I don't know, maybe say T, and this is position T plus 1. So once again, from this position, control moves to Z. Like from here, the control moved to Z. Similarly, from here, the control moved to Z. And from Z plus 1, it returns back to T plus 1. So the sequence looks like this, that at Y, it jumps to where? It jumps to Z. Z is the start of the function F. Now, inside F, at Z plus 1, which is its end, there will be a command called return. In 8085 assembly, this is RET in 8085 assembly. Now this is return. What is meant by return? Return to the address indicated by the call stack. So whenever y it jumps to z is, or rather it basically when it jumps to z in the call stack. Now let me draw that separately with another sort of a, let's use green and this time. In the call stack, what is written is y plus 1. When return is, the return function here is executed, it looks up, basically looks up the call stack, and it returns to whatever has been given in as the last entry. You can imagine stack, so it's LIFO. Whatever came in last will come out first. In this case, we only have y plus 1 as an address. So basically here, the first one will be, when it comes to z, the first return will be to y plus 1. So the control will jump from here to y plus 1. Again, it starts executing, and this is no longer in memory. Now once again, at the position t, so at the position t, there is again it jumps to z. So when it comes from t to z, and again at z plus 1, it returns to t plus 1. Now what will happen? Once it jumps to z, and immediately before it jumps to z actually, it returns the, or it stacks out, or stacks in rather, stacks in the return address t plus 1. Now this was executed already. Now for this particular run of the f function, at z plus 1 there is return again. What will the return statement do? Look up the stack. What is it? T plus 1. So now this control will be returned to t plus 1. Again main will start executing. Consequently, let us say main ends here. Let's call it m dash. Main exits here. What happens at m dash also, there is a return statement. But who does main return to? Basically, it returns to the calling program. In case of f, the calling program or function was main. The calling function was main. In case of main, when it exits your program, so it must go to the program that was calling it, and that is actually the operating system. Gives control back to the operating system. The use of the stack will be slightly more clear if we have multiple calls. Imagine main, all the functions now is calling f somewhere, then some other, then it ends. In f, some statements are there, executable statements are there, whatever statements there, and then there's a control, there's a function called to g, and then some other statements may be there, and then it ends. In g, which is another function, so some statements are there, and it ends. That means With each call to F, you are calling G also. And then from G, you are returning to F and then you're returning to main. So how is this call stack used there? Let us draw the threads as memory basically. Let us say this is main. Sorry. Let us say this is the entire memory. This is F, ends here. This is G, and G obviously ends there. And main. So this is, let's say, F dash. Sorry, I'll do it here. F dash. This is G dash, and G starts off at memory address. Actually, this is not in letters, but in numbers. But I'm just using to be on the to make it simply to make it simple. I'm just using G dash, G start and G dash is end. F is start and F dash is end. Main is here. Main starts at, this is main. Main starts at memory address M and finishes at memory address M dash. Now, as you can see here, in the middle there is a call to G. So this is called to G. Let us say this one is F plus say 5. Then in that case, this one automatically is going to be F plus 6. This is the return from G. Similarly, let us say that an M at M plus say 10, there is a call to F. So the return from F is at M plus 11. Again, there is a call to F at M plus 20. What do I mean by 10? M is this starting address plus 10 addresses. This is plus 11 addresses. This is plus 20 addresses, so on and so forth. So plus 20. So another call to F, and the return will be at M plus 21. Just as we had here, we were calling F at line number Y. So we are coming back at line number Y plus 1. We are calling F at line number T. We were coming back at line number T plus 1. Similarly here, let us talk, say, line numbers, let's say. So we are calling F at line number M plus 10, where M is the starting of the main. So at M plus 10, we are calling F. So we are coming back at M plus 11. We are calling F again at M plus 20. So that we are coming back at M plus 21. Here at F, in line number F plus 5, where F is the starting of F plus 5 we are calling G. So we are coming back at F plus 6. Let us make it a bit more clear. Coming back at F plus 6. And G starts up at line number G. And then there is there. So the way is asking whether one difference between the function call and the return. That's very simple. You call the function at a line. So you jump, as I showed here, that you jump from this line to F. Once F finishes executing, you come back to the next line and start executing. That's all. That is why wherever the call is, you come back as a line number, the next line number. Now, so all of it is there. Now, if we also denote the line number as the addresses, then the call stack will be populated as follows. So at M plus 10, there is a call to F, and the call, let us draw the call stack here. What will be written is M plus 1. Fine. At F, we have another function call. So, and that is happening specifically at F plus 5. There is a call to G. Now, G will have to return somewhere. And this is F plus 6. So, what will be written is F plus 6. Now, the first return occurs at G. As usual, the return statement or the return command, whatever way it is designated, that looks up the call stack. So this is the call stack. That looks up the call stack, and what does it find? F plus 6. So from here it returns to F plus 6. Sorry. So F plus 6 is now popped. Now the next return statement occurs at F. So let us say the next return statement occurs at F dash. And once again, what does the return command do? It pops the call stack and goes to whatever address is available in the call stack. So the call stack is only containing one, because we have already popped A plus 6. We have only got M plus 1 here. So we pop it. So now the next return will take the control back to M plus, small typo here. This would be M plus 11. Sorry, M plus 11. So it has been popped, and now so we return the control back to M plus 11, and the stack is now empty. So again, when at, what is that, Anonna? Oh, acha, acha, okay, okay. Acha, anyways, so now next, another call to F happens obviously at M plus 20. So there the call stack now, which is now empty by the way. So this is another run of the stack. So now it is written with M plus 21, and when it goes to G once again, now this obviously F is stationary in memory. F is obviously stationary in memory. So it is again written with A plus 6. So the first return occurs with our G returning it. So pop by, so we pop it. This is by the function G. So return to F plus 6. And then the next pop is done by the F function. When it returns, we will call it pop by F, and in which case it returns to M plus 21. So basically from here, the next one, which I'm drawing it with a dotted line, this will be returning to M plus 21. So as usual, from M plus 20, let me draw the dotted line. We had come around to F, and from F we have returned to M plus 21, and from F to G, obviously it is this green line here. At F plus 5 we jump to G, and then we come back. This is a static thing, it's always there. This is the mechanism of, and this is how we use the call stack. And after that last pop is there, stack again becomes empty. Now not just that, there is something else that you must note. You have got already the concept of the memory registers. Now these registers for one processor, so for one processor it will be the same one. So let us say, just one sec, chup chup dok, chup chup dok. So let us say that this is the processor here. Okay, let me just try to be closer to me. Control unit is there as usual, and basically the accumulator is a part of it, of the ALU in general, and there are the other data registers are there. So let me just draw them out with say green, light green. Just use light green for this. All the data registers are there. So this is the register 1, this is the register 2, register 3, register 4, register 5, register 6, register 7. Plus then there is a program counter, the instruction register, and the status register, which is also called, by the way, it is also called the program status word, because it's a word of memory that contains the status of the program, whether it's produced a 0, or it produced a carry, or it produced a sign which is negative or positive, like that. So all of these are there. Besides that, there are some other registers, so other registers may be there, others also. At any point of time, the program state, it means the value of all these taken together for one particular program. So at the time of running of a program, at any point of time, if you just freeze it, what is the value of R1, R2, R3, R4, R5, R6, R7, program counter, instruction register, program status word, other registers that are used, all the registers that it is using, as well as the accumulator. What is the status of all of that? That means what is the value contained in all of that? So value contained in these registers, this is basically the program state. Now let us say that, now obviously program state, it actually depends from routine to, that means that you say, when I say routine to routine, means from function to function. So but when you are dealing with say main, some registers are being used, the program counter is at one point of time, at one value in time, and then the instruction register has got something, and then the PSW has got something and something, then you shift to F. What will happen to all these values that you need to run main again? So these are then put on the another part of stack. So stack the state of the current subroutine read function, and when you do that, before jumping, okay, that is before jumping to another subroutine, you stack the state of the current subroutine. So in the previous example that we showed, this is how it happens. Main is calling F, is calling G, which is returning to F, which is returning to main, okay, like that. This is main, this is F, this is G. Now here the way it would have happened is, let us say this point is x, this point is x plus 1, this point is y, this point is y plus 1, and so on and so forth. So what will happen is the first of all, at x, before we jump to y, first of all, store mains, sorry, the mains state to stack. Next, store return address, that is x plus 1, to call stack. Next, jump, that is in our case jump to f. At y, then what will happen? Simple. 1, store, so if state to stack, then store, and the return address is y plus 1, store y plus 1 to call stack, then you jump to g. Now what will happen when you come back? So now what will happen when you come back? Okay, just one sec, Divya. So now what will happen when you come back? At y plus 1, we restore f state to processor. So we can start again, and at x plus 1, we restore mains state to processor, so that we can at f we can continue from where we left, and then again at main we can continue from where we left. Okay, Deepa, go on. Please ask. Yeah. It is the return address followed by f. X plus 1 will be restored. Yeah, it will come back to x plus 1 after f is finished executing. Yes. I'm saying yes, you're right that x plus 1 will return to x plus 1 after f will finish executing. Yes. The address of f is obviously that is in memory. So at x there will be a jump. So wherever you are jumping, that means the control is moving there. That will be stored by the program counter. No, obviously not. Address of f will be stored in call stack, where at the point of y plus 1, when there is at the point, rather at the point of y, when there is a call to g. So if you followed this other one here, okay. So when you are going to another function, wherever you are going to another function, the call stack is used for the return address. So here also, here also, when you are at y and you are going to jump to g, you store y plus 1 on the call stack and then you go to g. So when g is finishing and the return statement is encountered, then y plus 1 is where it returns, and at y plus 1, okay, before it starts executing, at y plus 1, this return statement would reinstate if status, that is if program state in the computer, that is all the registers etc that you were storing in the variable stack etc, instruction stack, variable stack etc. Okay, so those will now be reinstated into the exact thing that was there, the exact snapshot of all these registers that were there before the call to G, that would be reinstated to the processor, so that from y plus 1 it will be continued uh, that is, this state will now be continued forward with the effect of G in place also, that is to say. Similarly at main, when we call function, this is the first one that we call function f from main. So when we call f at x, so the call stack will be used for x stack x plus 1. The program state of main will be stored in the variable and instruction stack. Whatever the the whatever the what can I say, the variable, rather whatever the values of r1 r2, whichever state that was being used, that whatever it was, that will be stored in stack for main, whatever it was that we stored in stack, so that it can be reinstated afterwards. And then we'll go to f, and before we go to f, obviously at x there'll be a call to f, and whenever there is a call to f, basically it's a jump statement, so the program counter where the control leads to will be loaded with the call to x. But before that, see, if the program counter is just left with an address, the program counter, if it is just left with an address, then what will do is it'll just go there, the control will just go there and start executing. But with a jump, however, it's a special kind of an instruction, that's why I've always said jump. What will happen is, first the program state will be stored in stack, then the return address will be stored in the call stack, and then the jump will occur.